Uh, I'm audible, right? Clearly?
Yes, the recording has started.
Yeah.
So
All right. So, just for logistics, Kai, do I have around 45 minutes or 50 minutes for presentation or lesser than that?
we don't have the limit for times. Your some meeting will go continue until maybe 2:30, as late as 2:30. But if you can finish the technical most of technical content before 2 p.m., I will see most of people will stay with you.
Okay. I appreciate it. Hello, everyone. My name is Nilanjan Ray Chaudhuri. I am a professor with the Electrical Engineering Department at the Pennsylvania State University. And this work was done in collaboration with my PhD student, Fayaz Hussain, and Professor Alok Sinha, who is a faculty with the Mechanical Engineering Department at the Pennsylvania State University. The work was funded by Tesla, and we also received some technical inputs from Tesla's side. So we are looking into the problem of fluctuations in the AI data center load profile. The load profile, a typical load profile is shown here in this diagram where you see you have two key phases or periods. One is the rest period, another is the compute period. And this transition means you have a sharp and significant change in power consumption, average power consumption between the
Hi,
compute
Slavan.
period and the rest period.
K- I'm doing good.
Was there a question? Okay. I'll continue. And during the compute period, if you zoom in, you will see that there is a periodic or near periodic or quasi-periodic fluctuation that typically is observed. You can also have stochastic variations on top of this. So how do we characterize these near periodic or periodic fluctuations that we have heard of or we have observed in the field? From rest period to compute period and back, we see typically slow variations or low frequency variations ranging in the electromechanical oscillation frequency range, 0.1 to 1 hertz. The faster, relatively faster frequency variations are in the compute phase, which is in the subsynchronous range, could be in the range of 5 to 50 hertz, or it could be within a narrower band. So, of course, it has negative implications on the reliability of the bulk power system if it is connected to the bulk power system, or if it is an islanded system connected to a local generating plant, it can have negative implication on the reliability of that integrated system. And some of these aspects that can negatively impact the reliability include voltage flicker, frequency regulation issues because you have significant ramp up and ramp down in power. It can also excite the modes, existing natural modes of the system, and that's probably the context of this working group, Forced Oscillation Task Force. So here we are going to talk about interaction with synchronous machines, and we are primarily going to focus on torsional modes, exciting torsional modes, because of these forced oscillations in the compute phase of AI data center loads. And the motivation is to fill the gap that we have in industry in terms of the knowledge gap, so far as identifying a framework to assess the impact of such fluctuations on turbine generator shaft fatigue life is concerned. And the other aspect that we are looking into is how do you come up with a limit that you can impose on these fluctuations from the utilities side so that these will respect the allowable fluctuations at the generator's terminals, and as a result will not endanger a shaft breakage or reduction of shaft fatigue life. So we know that there are multiple types of natural modes in the system. I alluded to a few of them: local modes, inter-area modes. We heard about this from the previous presenter as well. There are IBR-induced subsynchronous oscillation modes in the system, but there are torsional modes and blade vibration modes. Those are there inherent to a turbine generator system. Typically, here the focus is on thermal generators, and in thermal generators, you have usually different stages of the turbine: high pressure, intermediate pressure, different stages of low pressure, you have the generator rotor, and you have the excitation systems rotor. And these are coupled through shafts which are not perfectly stiff. And as a result, these masses can rotate at different speeds following this kind of forced oscillations, and there will be twists across these shafts. And then because of that, there will be shear stress in the shaft, and then that can lead to cumulative damage or reduction of fatigue life. So what are the stakeholder questions? The stakeholders are asking, if I am given a AI data center load profile, will the nearby generators shaft fatigue life be negatively impacted, right? The other side of the spectrum is, if I have an interconnection queue and I have certain AI data center projects, which are the buses or locations that I would definitely want to avoid in order to make sure that we have mitigating measures that will be feasible. And then if I have multiple such AI data center loads in the system, how do I optimally determine the limits on the AI data centers fluctuations? Finally, how do we check compliance? So we tried to answer some of these questions in our work. And in order to do that, the first contribution of this work came up related to the framework that would assess the impact on fatigue damage of the synchronous machines from such forced oscillations emanating from AI data center loads. So far as torsional oscillations are concerned, primarily that's the focus. We have then framed a frequency domain approach to conservatively determine the limits on allowable fluctuations at the AI data center load terminals in order to respect such limits to ensure that your fatigue life will not be negatively impacted at the generators. And then finally, we have proposed a modeling framework which is based on dynamic phasors, and that is used to validate the proposed limits using nonlinear time domain simulations in a multi-machine systems. So this last contribution on the framework does not affect the outcome of the proposed method to determine the limits on the AI data center loads, but it is a validation framework, and one could choose to use much higher fidelity models, let's say using EMT simulations, which faces of course challenges when you try to run such simulations for larger scale systems. Wide area EMT simulations are still challenging computationally. All right, so with that, let's go into the details of the first contribution, which is the impact assessment framework. I'd like to spend a little bit of time on this particular slide. I mentioned that there are multiple masses in the coupled thermal turbine generator system. So how do we model this system? The best thing would be to develop a continuum model of it. That would be a wideband model. That model would be able to capture both the subsynchronous and going into the supersynchronous range. But since our forced oscillation spectrum is in the subsynchronous range, that's under consideration here. With that assumption, we have considered a lumped mass model. So what is the mechanism that's taking place here? You have AI data center load at a particular bus in the grid that is undergoing this kind of periodic or near periodic fluctuations, transiting from rest period to compute period, and you have subsynchronous forced oscillations during the compute period. That fluctuation propagates through the transmission network, and that appears as power fluctuation and in turn electromagnetic torque fluctuation at the generator's terminal, let's say TE being the electromagnetic torque. That will in turn induce torsional oscillation or twists in these shafts connecting these masses, and that will be reflected or captured through this differential equation of the lumped mass model of this turbine generator shaft system. So these are standard state variables, delta and omega, And the three key parameters that determine this model are the inertia constants of these masses, denoted by H sub r for the rth mass, and the stiffness coefficient of the shaft, which is Kr for the shaft connecting the rth mass and r plus 1th mass, and the self and mutual damping of these oscillations. So those are also important terms, d and d bar. Now, how does these angular displacements deltas get translated into the tensile stress? So we need to calculate the maximum tensile stress in this shaft. The shaft has, let us say, a radius of RR and length LR for the rth shaft section. And you have the angular twist at both ends being theta r and theta r plus 1. So theta r plus 1 minus theta r is the twist angle, the difference between these two. And the maximum tensile stress, assuming that this shaft is in pure torsion, would be the shear stress. And that shear stress is sigma r, that is proportional to this twist angle, which is theta r plus 1 minus theta r. And that depends on the proportionality constant, depends on material property. And where you see this term G, which is shear modulus of elasticity of the material. For steel, for example, this is 83 gigapascal. And it also depends on the geometry, the ratio of the radius and the length of the shaft. All right, so now we are able to show how this forced oscillation that you have at the AI data center terminal gets transmitted through the system and appears as electromagnetic torque at the terminal of the generator, and then that goes into creating oscillations in the tensile stress or maximum tensile stress in this case, which is the shear stress. Let's say this is a periodic fluctuation that you observe. It won't be, of course, monofrequency. There could be multiple frequencies involved in this oscillation. And you can then calculate the average value or the mean value sigma m, and also the amplitude sigma a. So this shear stress is also proportional to the torque. Okay, it's called coupling torque. And this is the particular formula that you see here, relates the coupling torque with the shear stress. Someone was asking at some point that whether torque is something that one needs to monitor. Yes, end of the day, the shear stress is going to be proportional to it, proportional to the torque. Okay, so one observes, let's say, this shear stress, and the shear stress, hypothetically, if we assume that the mean shear stress is 0, in that case, we can use the so-called SN curve, which is also called the Wöhler curve or torsional fatigue characteristic, which plots this sigma A in the y-axis versus cycles to failure in the x-axis. And here you observe a horizontal portion of this curve with this variable SE, which is known as the endurance limit. Okay, and it's also called the high cycle fatigue limit equivalently. So the idea is that if one can limit the amplitude sigma A of the shear stress below the endurance limit, and here I'm talking about mean stress being 0, this is only applicable when mean stress is 0, then practically there will not be any fatigue damage. So just to be on the same page, what is fatigue damage? Fatigue damage is a process of progressive, localized, permanent structural change occurring in the shaft material, subject to fluctuations which may culminate in cracks or complete fracture, known as fatigue. Okay, so it's a cumulative effect. So the idea is, if you have your amplitude below this endurance limit, you practically won't have any loss of fatigue life. But we know that the mean stress mean shear stress will not be 0 because the machine will operate at a nominal point, usually let's say at rated power output, and there will be a constant twist angle that will be present during that steady state operation, and that will give you a non-zero sigma m. So when that happens, one needs to use an augmented modified Goodman diagram. This diagram plots sigma A, or amplitude of shear stress, on the y-axis and the mean shear stress on the x-axis. And you see that there is a shaded region in this augmented Goodman diagram. That shaded region will be called the safe region of operation. If you operate within this region, practically you will not lose your fatigue life because of these torsional oscillations. Now, how to use this modified Goodman diagram? The idea is to first determine what is your mean shear stress. Let's say that is sigma m0. Get that point on the x-axis, draw a vertical line, and wherever that line intersects this boundary of the shaded region, for example, in this case here, this will give you the value of the endurance limit. So that will give you the endurance limit, and you will need to operate below that limit. Well, I probably should not say that I should not call that endurance limit, because endurance limit is SE, which is unique, which is for zero mean stress. I should say that this is the allowable fluctuation amplitude of the stress below which you should operate. I should not call that endurance. Okay, but that's how you can use the augmented modified Goodman diagram to determine the allowable amplitude of maximum tensile stress, and that will play an important role as we try to determine the limits on fluctuations on AI data center terminals, and also, of course, evaluate, if given an AI data center load, whether you are endangering the fatigue life because of the torsional oscillations. As an example, you see, if I have a power profile fluctuations here, and if that was subject to the multi-mass model, by the way, this framework that I just showed you, here you do not need to consider anything so far as the rest of the grid is concerned. This is completely considering only the lump mass model, multi-mass model of the turbine generator system. And here, all we did is to subject this electromagnetic torque variation at the terminal of the generator to see if the stresses cross the maximum allowable stress. These stresses are per unitized with respect to the maximum allowable stress. So the maximum allowable stress appears as 1 per unit in all of these plots. And these are the shear stresses in different shaft sections of this multi-mass turbine generator system. And here you can see that this is within the safe limit. This is less than the allowable fluctuation limit, and we are good. This is another example where we played back the profile from NARC's large loads white paper, and we can see that in certain shaft sections, this goes over the allowable limit. And so you are endangering your fatigue life of the multi-mass turbine generator shaft system. All right. So what is the conclusion in the proposed framework? To assess whether a given AI data center load profile can risk the fatigue life of your turbine generator system, you run time domain simulation with multi-mass model, and you calculate the shaft stresses based on the shaft dimensions and material. And based on mean stress calculation, you will be able to get the allowable fluctuation so as not to negatively impact fatigue life because of the torsional oscillations. And then you can evaluate by running your AI data center load profile at the terminal of the generator to see if that can impact the fatigue life. Now, the next part of the question was from the utility side, how to impose limits on the AI data center loads. assume that we have a BPS, a bulk power system. And for the time being, let's assume we have only one AI data center load. Intuitively nearby or electrically nearby synchronous machines will have higher risk. So a framework is needed how to consider imposing a limit on the fluctuations of this AI data center load. So here we went into a frequency domain approach and just trying to show this schematically, the thought process. We consider AI data center load power fluctuation at a particular bus. And then we calculate what we call an algebraic interaction factor. You can consider these to be gain factors. What is this algebraic interaction factor? So I'll just skip and go to this slide to pictorially illustrate it. So let's say we have a system like this, and you have an AI data center load at this bus. So if I change the load at this bus, how much of that real power change gets reflected at the generator's terminal, right? So intuitively, here you have G3 and G4 electrically closer, and you will probably see larger change in the generator G3 and G4 powers compared to G2 and G1 power. You can run a phasor-based dynamic simulation to create a step change and evaluate this ratio of change in the generator power with respect to the change in the AI data center's load power, and use that as the interaction factor. And the paper that we have co-authored, and which is available in the archive, the link is there in the last slide. There we have proposed a modified load flow to be able to calculate these interaction factors. So basically, this is an amplification factor from the AI data center load terminal to the generator's terminals so far as these variations are concerned. Of course, this is algebraic, and we have assumed that the ratios are constant beyond 5 Hertz. And let us say we have in generators, and these are some example numbers of interaction factor from the AI data center bus to other generator buses. Now, how do we go from there to evaluating the shaft stress in a meaningful way, which is, in our case, conservative, so that a blanket optimal limit on AI data center loads, independent of the load profile, can be proposed or imposed by the stakeholders, in this case, let's say the utility industry. That was our objective here. So here we considered, let's say you have these fluctuations at the AI data center loads, it gets amplified, or in this case attenuated, right? Because these are less than 1, and then you get this load profile and you do an FFT, and let's say you focus on the subsynchronous range, and you consider a transfer function. So this FFT is considering the power or electromagnetic torque at the terminal of the machine. And then I showed you the multimass lumped model. That lumped multimass model can be linearized, and you can get the transfer function of input being the electromagnetic torque and output being the shaft stresses at different sections of the shafts. Okay, so here, for example, you see different colors of Bode plots showing, for example, the blue one is between HP and IP, high pressure and intermediate pressure turbine section, and others, and similarly the phases. So these are the, for example, different frequencies you can sweep along, and you see, let's say at this particular frequency, you have, let's say, gain 3. This is just a number to quantitatively manifest that this is the highest gain, and pictorially you can see this is where the highest gain is. And these notches, of course, will coincide with the torsional modes, modal frequencies for this particular machine. Now, we have mathematically analyzed this and created sufficient conditions. And the moment you create these sufficient conditions, they will be taking conservative assumption such that the shaft stress limit is not violated. That has been the goal. So translating that pictorially, what we first focus on is what is the maximum amplification you see across all shaft sections across the entire frequency range, so far as subsynchronous frequency range is concerned. Let's say that is 3, it's just a number here. And then the next thing that we do is we consider that highest gain or highest amplification across the entire range, subsynchronous range. Next, we assume that the phases of this multi-frequency power fluctuation at the generator terminal can be adding up such that you have the worst case amplification of the amplitudes. Okay, so that is the other assumption. So with that assumption, you get the shaft stress in this form. So this is a shaft stress, you calculate it in this form, that you have the interaction factors multiplying that by maximum amplification, which is, let's say, 3. That is multiplied by this FFT, which is the sum of the components of interest. So at the load terminal, right? The sum of components of interest at the load terminal, FFT of the load terminal power. So FFT of the load terminal power multiplied by the interaction factor multiplied by the maximum gain, that should give you the shaft stress, the worst case shaft stress, independent of which frequency content is there. And that shaft stress amplitude, which is sum in the form of sum of FFT components of shaft stresses, that should be less than the maximum stress amplitude. And this maximum stress amplitude we obtain from the modified Goodman diagram. So just translating that into this inequality gives you what is the sum of all frequency components or FFT components of interest in the load. That should obey this limit. And this limit will be binding as long as you choose the minimum across all shaft sections in all generators, right? So with this, so this was shown mathematically and the inequalities were shown mathematically. So here just graphically showing this, that interaction factors, again, you can calculate it from the dynamic simulation, phasor-based simulation, positive sequence, fundamental frequency simulation, let's say using PSSC or PSLF, or using modified load flow if you code it. And then you can consider the maximum amplification. And that maximum amplification factor needs only a very simple code because you just consider the lumped multi-mass model of the generator. And then you have the maximum stress amplitude obtained from the Goodman diagram, and minimizing this or taking the minimum value across all generators and the shaft sections will give you the limit, the bounding limit on not the peak-to-peak amplitude, but sum of all FFT components of the AI data center load under consideration. So this is the thought process, this is the philosophy. This is an example of the terminal power output P of a generator and its allowable variation in frequency domain. As we see, the x-axis is the frequency. As you vary the frequency, you see the notches. Of course, these notches coincide with the torsional modes. And this is the place where you have the highest gain, okay? And that highest gain is corresponding to allowing 1% of the electrical power output at the terminal, sum of FFT components being 1%. Now, I'm not going to go into the details of this other part where we took into consideration a queue and multiple AI data center loads can be integrated into the system. The key message I want to convey here is the proposed approach takes into account 2 steps. One is a bus screening and ranking, where you would probably rule out certain buses based on your constraints that you may have in your utility. And then we want to determine optimal limits of allowable fluctuations. And this approach follows a simple linear programming, and which can be again coded in Python or some other software platforms, but this should be very simple to do. And this, the outcome or the output is to get the optimal fluctuations, allowable fluctuations. The objective essentially is to maximize the maximum allowable variation at the AI data center load. So you want to give them the maximum opportunity in a sense that they are not unfairly restricted in terms of the allowable fluctuations at their terminals. Okay, and again, everything here is sum of 50 components. The restrictions that we are talking about is sum of 50 components. So in conclusion, we have come up with a highly conservative assumption so far as site-specific limits on some of 50 components of AI data center loads are concerned. The reason behind this approach is that you can determine these limits independently, and the limits are going to be independent of the frequency content of your load fluctuation, and that aids this kind of assessment so far as utilities are concerned. And I also briefly mentioned what happens when you have multiple AI data center loads and how, assuming the worst case cumulative buildup of different frequency contents, you can impose an optimal limit and also not negatively or not penalize any AI data center load site unnecessarily. The other factor we considered here was limits on bed vibration. That is another source of fatigue. There it was considered indirectly, taking into account the safe frequency range of operation, considering the ANSI standards. So this was not explicitly modeled through any dynamic model, but it was considered indirectly through the safe frequency range of operation, and we considered the frequency limit taking into account a safe frequency of operation, which is beyond which you cannot even allow the generator to operate instantly, even for an instant. Okay. All right. So this is a paper that has been submitted for peer review, and it's publicly available in the archive. And showing you a couple of slides on results. The final contribution that I mentioned was how do you validate this? One challenge is, of course, taking into consideration EMT simulations, computational challenges when it comes to simulating relatively larger bits. We understand that SSR studies are one of the examples where you regularly run EMT simulations, but the rest of the grid that you consider in such simulations are usually limited to certain close by regions. But here that will be challenged. You may need to consider a larger portion of the grid. So we took into account this challenge, and we proposed to use the dynamic phasor framework. And the dynamic phasor framework was first validated using IEEE first benchmark model. We chose this model because it takes into account the multi-mass shaft sections of the turbine generator system, and also dynamics of the transmission network, because you need to consider the series compensated lines dynamics. And this is a comparison between the EMT model, which was in MATLAB Simscape, and the dynamic phasor model was also built in MATLAB Simulink from first principles. And the overlap shows a reasonable match between these two frameworks. Once we got a decent response from the dynamic phasor model, with that confidence, we moved forward and we considered two systems. First thing I wanted to highlight is this is a well-known 68-bus NETS NYPS system. The green generators were considered to be multi-mass, considered to be with multi-mass models. This system originally does not come up with a multi-mass model. So we took into account two sources. One is the IEEE first benchmark SSR model, get the multi-mass model data. The other is an example from Kundur's system. And then this is a heat map of the interaction factors. The blue end is low interaction factor, and as you move towards the red side, you have higher interaction factor. Higher meaning you have more coupling, stronger coupling between the AI data center load terminal and the generators terminal. So let's say if you have all candidate buses in the NETS system, which are here, what this message conveys, what this figure conveys rather, is you are fine to analyze the NETS region of the system. You do not have to consider, again, the NYPS part of it, and the interaction factors will show you that. We did time domain, nonlinear time domain simulations, ran LP, and you can see those results from the paper. But I just wanted to highlight something on a relatively larger system, which is a synthetic 2000 bus Texas system. And again, a heat map of algebraic interaction factors. When you consider only the 39 generators in zone 1, it tells you that you probably don't need to consider beyond zone 1 and a small part of zone 3 for your analysis. You don't need to consider this entire 2000 bus Texas system if you are trying to evaluate the impact of AI data center loads on these 39 generators which are in zone 1. Again, this is not a dynamic model. So we don't have dynamic model data. What we did is we assumed that at each generator terminal, 1% power variation, 1% being the sum of 50 components, is allowable. And with that assumption, we ran the LP considering 13 and 14 candidate buses respectively. And you end up seeing these box plots that shows if you have 14 candidates, you have, this is the box plot with a median value hovering around 18 megawatts for the allowable fluctuations at the AI data center load terminals. Sum of 50 components. Again, it's a sum of 50 components. You have 13, which is less number. You have slightly higher allowable, which is also intuitive. Yeah, so end of the day, this will give you the chance to calculate these limits optimally using the LP. All right, thank you. And look forward to your questions.